Hi and happy Thursday, everyone. My name is Bill Garibaldi, and I'm a member of the CUIIC Education Committee, and I work with today's presenter, Dan Gonser at MTE Consultants. I'm happy to be able to host this CUIIC webinar for you today. So CUIIC Academy, as we're calling it, has a number of events. They're organized by the Canadian Underground Infrastructure Innovation Centre, CUIIC, at the University of Alberta and in association with Benjamin Media. The CUIIC Academy offers classes, courses, webinars, and events to help further underground infrastructure educational opportunities across Canada. The webinar series, one of which you're watching today, covers a variety of what we feel are pressing topics related to the underground infrastructure sector. Speakers include industry-leading professionals who provide a monthly free educational webinar, and the webinars are followed by a question and answer period. So although that the webinar today is to run from sort of 1 to 1:30. From 1:30 on is available for questions, 1:30 to 2, I should say. So join us for the on the third Thursday of each month at 1 p.m. for the next or the follow-up webinars. And if you want to view the schedule, you can see it at CUIIC.ca. I want to thank today's, I shouldn't say today's sponsor, I should want to thank the series sponsor, the webinar series sponsor, MPipe, for sponsoring the 2023 CUIIC Academy Webinar Series. And if you're interested, if your company's interested in sponsoring, please feel free to contact Hannah Stokolich at CUIIC.ca for more information. Please join us next month in Mississauga for the Pipeline Rehabilitation Academy. That's a 2-day course-style academy on March 21st and 22nd. And for our webinars, there's a spray-in-place pipe, spray-applied systems for trenchless rehab webinar on March 23rd. And then on April 20th, join us for the microtechnology for utility installation webinar. That's microtechnology for utility installation webinar. I sort of screwed that up. And for more information on anything related to the Canadian Underground Infrastructure Innovation Centre, check CUIIC.ca. Now I'd like to introduce my colleague, Dan. Dan is the Geotechnical Division Manager at MTE in Stratford and in Kitchener, Ontario. MTE Consultants is an employee-owned, multidisciplinary engineering firm with 5 offices across Southern Ontario. Dan performs geotechnical exploration, analysis, and engineering for a wide variety of municipal, residential, commercial, and industrial projects. His project work includes analysis of data for the design of deep and shallow burying foundations, utility installation, pavement design, and slope stability analysis. Dan graduated from Queen's University in civil engineering and is a registered professional engineer in Ontario. So Dan, I'll turn it over to you for how to read a geotechnical report. Thanks.
Thanks, Bill. So to give an overview of just what we're going to kind of be going through today, I will start with kind of why you need a geotechnical report, what it's useful for. We'll go through some borehole log examples just to kind of go through the basics of what is shown on a borehole log. And then we'll talk about how to scope a geotechnical investigation and different types of investigative work that can be done for a project. So to start, why do you need a geotechnical report? So the one thing I hear all the time is that geotechnical reports are all the same, and that they're just copied and pasted from one project to another. And I'm here to kind of tell you today that that's not the case. It's not just something that gets attached to a tender and nobody reads. They do provide valuable information, and you should be reading your report and making sure that you're following the recommendations that are contained within it. They're used throughout the different stages of a project. So in the planning stages, they can assist with route selection for a project or site design. With this, you can avoid challenges that may need problem soils on a site that would need special design considerations. You can just avoid those altogether. So for example, this project, this kind of borehole plan on the right was a project we were working on for sanitary trunk sewer route selection. So we were able to kind of review a number of geotech reports in the area of the different routes that they were considering. And then we filled in some of the gaps with a select number of boreholes just at kind of critical areas to assist in selecting kind of the best route. Obviously, there's other factors at play with that in addition to the soils, but yeah. So these can be done kind of as a preliminary, something like that, where we're just doing a limited number of holes or just even a purely desktop review study. During the design stage of a project, then typically we would be filling in the gaps from a preliminary study and really nailing down what all the conditions are on a site, whether there's unsuitable soils that need special design, whether you have groundwater, bedrock, whatever the case may be on the site. So we're typically drilling boreholes at a set interval or set spacing for the project, whether it's a building or a road reconstruction or whatever the case may be, to get a good picture of the conditions. And then at the construction stage of the project, really the contractors are looking at the geotechnical report to see what sort of equipment they need and what sort of production they can expect based on the soil conditions. The type of soils on a site will have a big impact on the workability. If they're going to be impacted by weather, the site on a kind of a silt and clay site, you may be shut down for 2-3 days every time you get a good rain, as opposed to a sand and gravel site where that water is just going to infiltrate away and you're going to be up and running as soon as the rain stops. So certainly has a big impact on that. And what are the key kind of elements in a typical report? Generally, they're going to be, most reports are structured fairly similarly, where you're going to have an introduction talking about the project, a discussion on kind of what was done for the investigation, and then a discussion on the soil, the groundwater, the bedrock, whatever the conditions that were found. And then following that, you're going to have your recommendations on what needs to be done to have a successful project. So whether that's trenching recommendations or bearing capacity for buildings or bridges or structures or whatever the case may be, that's going to be kind of in that main discussion and recommendation section. And then typically in the appendix, you'll have figures of the site plan, location plans, borehole logs, and any lab testing results that were completed as part of the project. So moving on to borehole logs, every consultant uses a different kind of template borehole log. So they all look a little bit different. Some have color, some are black and white. The location of the information may be in different places, but the kind of the basics of a borehole log are generally going to be pretty consistent, the basic information that you can find. I found just a kind of a random log here to kind of walk through the different information that you can find on a log. So on the left in this log, we have the soil conditions and the depth plot showing kind of at the topsoil layer, and then your various soil units going down. So this log is mainly comprised of kind of clay, silt material, silt and clay. It does kind of make it, there's a lot of different soil units shown, but it is somewhat consistent, and the soils are all kind of clay, silt material. The next column over, they show, they provide the sampling information and what's called the SPT end value. So you can see as they went down, near the surface, they were taking samples at kind of a tighter frequency and then opened that up as they got deeper. And then the SPT end value, that's a test that is pretty much the most common geotechnical kind of sampling method and test that we do. And what that is you're driving a 2-inch kind of metal, what's called a split spoon, into the ground. It's driven by dropping a 140-pound hammer, a free fall length of 2.5 feet. And we count how many strikes or blows it takes to drive it into the ground. So the more blows it takes to drive it into the ground, the denser the soil is kind of the correlation there. So you can see then, based on what's called the end value, the number of blows per foot, we have different terms we call it. So on the top chart here, we have for cohesionless soils, so your sands, gravels, and then on the bottom we have kind of consistency terms for cohesive soils, clay soils, where we're talking about the consistency. As you can see, the blows typically range from anywhere to from about 0 to 50. Typically, we stop the test at 50 blows, meaning that the soils are very dense. The only time sometimes we'll go up to looking for 100 blow material if you're looking for something to drive piles for say a bridge project or something like that. They're often looking for 100 blow material. The next column on the log is the shear strength. So that's specific for the cohesive soils that I mentioned, that your clay soils. So there's two different tests that are shown on this log. There's the values that are being provided with the small little triangles, and then there's the one set of two squares there. So the small triangles represent what's called a pocket pentrometer measured shear strength on this one, and it has an acronym there, PP, and then the squares are showing field vein values. So and there's two squares there. One is the initial strength, and then the second is the remolded strength. So what the pocket pentrometer is, it's kind of a quicker small handheld probe that you just stick into the soil and measure the gives an approximation of the shear strength. The field vein is then completed. It's a bit more intensive, so you push a 4-bladed device into the ground, and then you turn it to get the initial strength, and then you wait, and then you turn it again to get the remolded strength. So that difference between the initial and the remolded, it gives us the sensitivity of the soils. So a more sensitive clay is going to have a much wider spread between those two values, where there's something that is not that sensitive will have a much closer values. The next column on this log is the moisture contents. So you can see it's pretty typical to take the natural moisture content of the soil of each kind of sample as you go down. This can kind of give a good indication of the water table level in a soil. This particular log doesn't really show it, but oftentimes when you hit the water table, you'll see a big spike in the water content. You may go from 5 to 10% for above the water table to to 15 or 20% below the water table. As well, this log has the results of Atterberg limit testing on it. Those are the two bands. There's two of the samples have the little bands that it's showing the arrow to. And what those bands are showing are the liquid limit and the plastic limit. So the spread between those is the plasticity index. And the Atterberg limit is a kind of a basic lab is used to give us the plasticity of the soils, which is then used in our evaluation of the soils. Something that might have a real high plasticity is going to be more prone to swelling or squeezing, where as opposed to a clay that is low plasticity. In the next column, it is a different log here because I wanted to show a monitoring well. The previous log didn't have a monitoring well installed, but so this one shows a monitoring well with the water level. So that inverted kind of triangle shape is the typical symbol used for water levels. So you can see on this one, the water level, it's about 2 meters below ground surface. And this is obviously very critical anytime you're digging into the ground. If you're going to be excavating into groundwater, that groundwater needs to be controlled in some way. So depending what the soils are, will dictate what the method of dewatering needed. On this particular log, we're dealing with a saturated sand. So if you're going a significant depth into that, you're going to have a lot of trouble digging if you haven't dewatered it. Typically in something like that, you're going to need to proactively dewater it with like well points or something such as that, where you're lowering the water table before you excavate, so you can have a dry base to work on and complete whatever it is that you're doing. Something like the previous log where we're dealing with a silt and clay, even if you are digging below the water table, oftentimes in those type of soils, you can get by with just a kind of a sump pump in the corner of your excavation, and kind of periodically controlling the water as it slowly percolates in. And something to keep in mind with groundwater as well is seasonal fluctuations. So on this log, you can see that this water level was taken 2018, 09, 07, shown on the monitoring well there. So that would have been in September. Which is going to be the driest time of the year. So in this particular case where you have a water level 2 meters below ground surface in September, if you were going to start the project in April, odds are that water level is going to be a little bit higher at least. So definitely something to keep in mind, that just because your borehole log says your 2 meter deep excavation is not going to be in the water, that may not be the case at a different time of the year. So the next log I have here is a log showing some bedrock cores. So obviously bedrock is going to have a big impact on your constructability, and if you're going to be dealing with that. So some big critical things to kind of note on that is how thick your kind of weathered zone is. So on this particular log, you can see that the top kind of what I've shown in the box there is poor to very poor quality bedrock, which before getting into below that is fair to good, excellent quality, progressively getting kind of better quality as we go down. As well, something to note in this one, we have the bedrock is described as red shale with gray dolostone layers. So those dolostone layers are going to be a lot harder within that shale. So the shale in this case may be something that is able to be broken up quite easily with a rock breaker on an excavator, or but the dolostone layers may significantly slow them down depending on the frequency and the thickness and the hardness of those. The values that are kind of typically provided, the most common one is the rock quality designation, so your RQD, and that's what we use to base the very poor, fair, good, excellent quality rock. And so really it's just a good indication of what the strength of that rock is. It's the percent, and it's the percentage of pieces that are greater than 4 inches long divided by the total length of the rock. So in this case, this one that is shown in the box is the RQD is 53. So just over half is coming up kind of as big section pieces, bigger pieces. Some other things to look out for in a borehole log are conditions, I would say, are potentially unsuitable conditions. So something that isn't going to support structures, or we're going to have bearing problems even for potentially for pipes, depending on the conditions. So here we have a large buried peat deposit, typical of like kind of a swamp or wetland, but this one you can see it's underneath a pavement structure at the top of the borehole. So this one was a roadway in a kind of in a downtown area that obviously when the city was developed, they just kind of filled in a swamp area and buried this peat. But something that now going back, if you're installing a new manhole, you're not going to want to set that manhole right in that peat layer, because it's not going to provide support. You're going to have settlement after construction and a wonky manhole within a couple of years. So you're probably going to be needing to dig down deeper, replace it with some more granular bedding or something to deal with that peat. As well, 2 more examples I have here. On the left was a project that we encountered an old landfill that the municipality wasn't aware was there. So you can see the column on the right of that log shows the N values. They're 3, 2, 2, 3, 6. And the descriptions of some of the material there, clay, plastic, metal, glass, wood, brick. Again, something that's not going to be suitable to support really much of anything without movement after construction. On the right side, that is a log that was taken right on the lakefront of Lake Ontario. So back in the day, loose just kind of lake fill to get more land on the waterfront, using whatever really they could find, slag, brick, fragments, and obviously that material would have been placed kind of underwater with very little compaction and isn't going to be suitable to support really much of anything. The N values there are kind of 7, 5, 2, 2, 0, 2. So very low strength, something that is going to need to be designed around. So next, we'll talk about kind of how to scope an investigation. So the answer is it all depends on the project, what you need to do. A lot of that comes from what you're expecting the conditions to be and what the complexity of the project is. So are you going to have bedrock, high groundwater, or are you expecting to have kind of crappy fill or peat or something like that? And as well, what is the variability of the natural kind of geology in that area? On the right, these are 2 kind of pictures of surficial geology mapping that the 2 areas, they're only about 80 or 100 kilometers apart, but on the bottom, the surficial geology that is kind of in the Niagara region area is very consistent, generally kind of a clay material, whereas the other one is you can see in the Drumbo area, and it's very variable, where you may need a tighter frequency of borehole spacing just to make sure that you're not missing a pocket of sand and gravel that might be saturated that would cause significant problems with dewatering during construction. So some key things to consider when asking for a proposal. So what is the purpose of the investigation? Are you just looking to get preliminary or detailed design? So, and if it is detailed, you really need to provide your geotech engineer kind of as much design information as they have, so they can make sure their boreholes are deep enough and their spacing is correct. And you really need a clear definition of the scope if you're getting multiple quotes so that you can compare apples to apples. I just recently, we had a project and the client came back and said we were twice the price of somebody else for the project. And talking to them a bit further, the other consultant hadn't put in any monitoring wells. Well, I knew that the project was a sand and gravel area and that groundwater was very shallow, and we had a 6-meter deep sewer that we were going to need significant dewatering. So the fact the other consultant didn't have monitoring wells, I mean, it wasn't going to be a sufficient program. Some other considerations to take into account. One thing that right now in Ontario, at least, is excess soils. Is we have a new regulation for the movement of any excess soil from a project site. So we're on almost every project. We have an environmental engineer involved, and we're doing a soil characterization report to classify that soil and recommend where it can go. As well, do we need to do a hydro-G assessment? If we know dewatering is going to be required. Again, in Ontario, pumping over a certain amount, you're going to need a permit to take water. Something that like this well point system in the picture on the left, that almost certainly had a permit to take water, which is going to need a hydro-G report. So getting kind of all those other parties involved at the start to scope one cohesive program is really key. Skip aside. Something else, I do get a lot of clients ask, like, can we just dig some test pits instead of doing boreholes? Test pits can be good. They give you a very good view of the undisturbed soils, but they do have a very limited depth of exploration, and they make a mess. So boreholes can be a lot cleaner. We can get a lot deeper, and we get a lot more information about the strength of the soils from a borehole. Some other methods of investigation. This project here was I believe it was a sanitary trunk sewer that they were installing. And we knew that bedrock was relatively shallow along the stretch. So prior to our drilling, we went in and did a geophysical survey to map how deep the bedrock was along the corridor, and get an idea of where bedrock was going to be intersecting with the pipe. That way, then when we went out to drill our boreholes, we could position it kind of so we had some boreholes right where we thought we had the highest points of bedrock, take cores of that rock, and really get a much better investigation. Other methods of investigation, cone penetration testing, CPTU testing. It does give you a kind of a continuous profile with a lot more soil parameter information compared to a borehole, typically used on kind of higher complexity projects just because there obviously is an increase in cost with that. And then after the field work, obviously lab testing is typically done with any sort of investigation. So in the pictures here, you can see this is what's called like the two components of a sieve and hydrometer. So this is just a kind of a grain size distribution testing as well. We talked about Atterberg limits earlier and the moisture contents. Organic content is something that's going to be kind of real key information if you're looking at organic, like a peat deposit or a marl deposit that where you may need to know, yeah, there's a peat deposit, but how organic, like what is the organic content of it? And the results of that, like your typical grain size distribution, this is just a kind of a sheet showing the different samples that were tested. This is used by geotech engineers, just to confirm the visual classification of the soil that was made. And then in addition, there's different information we can glean from this, such as the frostability, susceptibility of the soils, the hydraulic conductivity. There's different correlations that we can kind of estimate how much groundwater is going to be, how fast groundwater is going to flow through it. Different items like that. Obviously, a sand and gravel is going to have a much higher hydraulic conductivity than a silt and clay. And this is the chart where you typically see kind of an Atterberg limit plotted. And what this tells us is we plot the liquid limit versus the plasticity index. So that gives us an indication of whether it's going to behave more like a silt versus a clay, and whether it's high plasticity or low plasticity. So there's the red diamond on this chart. It's in the high plasticity silt zone. So below what's called the A line, it is this kind of silt soils. Above the A line being the clay soils, and then the left side being low plasticity, the right side being high. So in conclusion, the Geotech report is something that is important. You should be reading it and not kind of trying to understand it. If there's anything you aren't understanding in it, I'd encourage you to talk to your geotech engineer, ask questions about it, and figure out what it is that they are trying to tell you, so that you're not missing something. So
that's perfect. Thank you, Dan. Okay, so we are going to go into questions. While we're doing that, rather than have this slide up, I'm going to advance to this slide. So if people want to get in touch with Dan to ask him anything after this, you can see his email address there. So the first question we've got, and some of these questions I realized afterwards, they might not be obvious as to where the questions were asked in your presentation. So you might have to do a little bit of investigative work here, Dan. So the first question was, what tools can we use to conduct a desktop study for scoping to QA and QC proposed geotechnical investigations?
Okay, so the first thing I always look at is surficial geology mapping. The area I work, Southwest Ontario, there's pretty good mapping from the OGS on a lot of the things. As well, in certain regions, I know in Southwest Ontario in particular, the Ontario Geological Survey has done kind of detailed soil mapping. So that's one source I typically use. Other sources are well records. In Ontario, any well that is installed, the well installer submits a record to the Ministry of Environment, and those are all available. So those can give you an indication of what is in the area and what you're expecting to find for soils, as well just other boreholes that, for me, other boreholes I've drilled in the area. So I know I did a project across the street from that. I'll pull up those boreholes. I know not everyone has access to years worth of projects, but that's something. Those are generally the main tools I use for that.
Okay, thanks. Now the next question here, what is a reasonable interval for boreholes for a trunk sewer project like in your slide 7? For long pipelines, we use 500-foot spacing. Smaller projects may have holes at 100-foot spacing.
Yeah, so it does depend on the project. Typically for kind of a trunk sewer spacing, we're using somewhere around 50 to 100 meter spacing, which in urban centers, generally for kind of small road reconstruction projects, we're generally looking at kind of the tighter end of that, 50 to 75 meters at the most. And then kind of your longer stretches of pipeline, maybe through like transmission lines and stuff, we may be closer to the 100-meter spacing, which is probably somewhat in line with the values.
And I assume, like you said earlier, if the area looks to have consistent material, you would take that into account.
Yeah.
Versus if it looked like Drumbo, like you showed us in your slides. Okay, what size bores are typical to collect samples for data in developing borehole logs?
Most of our boreholes, we're either using 6 or 8 inch diameter hollow stem augers. So that's just what all the drillers around us seem to have. If we are doing relatively shallow bores, sometimes we'll use like a 4 inch solid stem auger, but those the solid stem augers have some limitations to the soil types. They just are faster and produce less cuttings when you're dealing with shallow boreholes. So, but typically 6 or 8 inch.
Okay, and this individual had a follow-up question to this. If smaller diameter bores are typically used, how can it properly detect, say, pockets of soil containing larger cobbles or boulders?
It's a good question. Generally, we're looking at cobbles and boulders by the auger grinding through them. So you can kind of tell when you're drilling as they're augering down from one sampling interval to the next. You'll hear the augers will grind and it'll take a lot longer to get through kind of that cobble or boulder or whatever it may be. We're not going to generally be able to recover a sample with our sampler because, I mean, a boulder may be much bigger than the 2 inch sampler that we use, but there are methods of drilling that you can kind of collect those larger particles, but they're less common, I would say.
Okay, now this is the one of the questions I was talking about needing to become a little bit of a detective here. Is this done on core samples as well, or strictly for shallow jobs? So this came in sort of relatively early on during your presentation. I don't know exactly what it's referring to.
I don't.
You don't
Not
know
sure
either.
I know either.
Okay, well, we'll see if he submits another question. I'll keep an eye on that individual. Does a geotechnical report recommend a dewatering plan, including number and location of dewatering wells, to facilitate the construction when water levels will affect progress?
Typically, we don't get into those details. We are typically recommending that dewatering is going to need to be done, and a hydro-G report may recommend. You might provide kind of the expected pumping rate required, but at least in my experience, we try to leave kind of means and methods to the contractor's discretion, which would be the number and location of dewatering wells would be kind of up to the contractor, because there are different methods to achieve the dewatering, and I mean the dewatering contractors know best, and they know what's going to be more cost effective given a certain circumstance typically.
Okay. What is the maximum depth of a test pit?
The maximum depth of test pit, it really depends on the excavator that you have. So, I mean, if you just have a small backhoe, it may only be 8-10 feet or so. It also depends on what the soil conditions are. So, if you're in something that will hold up relatively vertical, they can generally dig a fair bit deeper. If you're in kind of a coarse sand and gravel, something that is going to slough off to be 1-to-1 sides, I mean, you can keep digging, but you're going to end up with a massively wide hole just to get deeper. As well, in something like a sand and gravel, once you hit the groundwater level, you're not going to be able to dig any further, because as you dig, it just the soil just flows in from the sides. So with a kind of a large, big excavator, you may be able to get 5 or 6 meters if you're in the right conditions. But it depends on the conditions and the size of the excavator.
Okay. Just 1 second here. Most geotechs stop when they hit bedrock. So how is the rock quality sample obtained? Did you hear that?
No, I did not hear.
It said, can you hear me now?
Yep.
Okay, sorry about that. Most geotechs stop when they hit bedrock. So how are the rock samples obtained?
So with our typical kind of hollow stem augers that I mentioned, those will you'll stop at bedrock. You won't be able to auger into the bedrock beyond kind of the upper weather zone. From there, we switch to like a core barrel that is like a diamond tip barrel. Basically, it spins really fast and drives down into the bedrock, leaving kind of the interior core, which is then pulled up and extracted. There's different width or diameters you can use for it, but it's like a diamond barrel core that cores the bedrock, and is then able to pull up the cores that it takes.
Okay. Next question. How accurate are the geophysical surveys?
Generally, they're relatively accurate, but they aren't something that you want to just stand on alone on. Typically, you'll want to then kind of calibrate it with boreholes. So you may think, because if we go kind of back to that, if I'll go back to that slide, let me just find it. What they're showing is changes in densities. So you can see kind of the color changes with the wave refractions for it. So what you want to do is confirm that color change is actually a change from soil to bedrock, and it's not a change from, say, sand to clay or something like that. So they're good, but they're not the only piece of that you want to rely on.
Okay, that's great. I was just looking ahead here, and there is a lot of questions. We are definitely not going to get through them all. So maybe you can answer the question as succinctly as possible.
Okay.
Is ground penetrating radar used for road structure investigation, for delineating asphalt, base, subgrade, etc.?
Yeah. So we've worked on projects like that. Again, it's something that you have to kind of calibrate, but it's good for seeing areas where you may have a small pocket where there may be insufficient granular base or subbase, or a really weak subgrade area. So it's a good thing to do to kind of pick locations where you may need a borehole, because there may be problems in that area.
Okay, when would it be typical for a municipality to require a geotechnical report for a development on private property?
We see different things with different municipalities. Most of the municipalities that we work in require it for kind of a site plan application for a new development, as well as like a draft plan application for new subdivisions. It really depends on the size of the project. Typically anything kind of a larger scale is obviously going to require it just for design in itself, but then the municipality will also be asking for it.
Thank you. How do you determine how deep the borehole should be?
For servicing kind of linear infrastructure projects, generally we're looking at the inverts and making sure we're going like 1 to 2 meters minimum below kind of our deepest excavations. Building projects, it depends on the size of the building. So there are different rules of thumb. If we're looking at kind of high-rise buildings, a lot of that comes down to where we think kind of there's going to be a real hard bearing layer that, or there's different rules in it, like going to a certain percentage of the applied stress, incremental applied stress from the building. You want to go to a depth that you're below that. It really depends on the project.
Okay. This is another one that I'm not 100% sure of the question. Where would settlement numbers be presented in the report?
So I assume this is kind of talking about expected settlement from whatever they're building, which would be kind of in the discussion and recommendation section. So if it's a building that you're talking about building and you're talking about the expected settlement under the foundation loading, that's going to be in the kind of the bearing capacity section. If you're talking about settlement from a large fill, like an embankment on a project, again, that's going to be, it's all going to be kind of in the recommendations discussion section of the project.
Thank you. If it from an underground infrastructure standpoint, you wouldn't be talking about settlement. You'd be talking more about providing base material or to stop settlement, wouldn't you? In that discussion area?
Yeah, you may be saying that a certain area doesn't have the support to stop to hold a pipe, and what you need to do to rectify that, whether it's more base or something like that.
Okay, thanks. Okay, this one here, again, I'm a little bit unsure of what the resistivity value from geophysical investigation is not suitable for the HDD, do you think? So what resistivity value from a geotechnical investigation is not suitable for HDD? Does that?
Yeah, I'm not sure exactly what to answer on that. I think it'd be project specific.
Okay, I'll just keep going. We've got so many questions. There's no lack of questions. What are the key tests needed for pavement layer assessment?
So to assess kind of the existing pavement conditions and whether or not they're strong enough, there are some further tests that I didn't discuss, like an FWD testing that can be done. As with most, you're going to still be doing some boreholes typically, collecting kind of samples of the existing granulars and seeing what the silt content is of those granulars to assess the drainage of those layers. Taking cores of the existing asphalt to see the thickness if you're doing an assessment of it, those sorts of things.
Okay. Do you have an example of a density test and how we can interpret it?
I'm not sure what the density they're specifically wondering about. If it's just like the SPT relative density that I was talking about, or if they're talking about more like a Proctor density. In terms of a Proctor density, I don't have one just readily available, but so it's kind of tough for me to just describe.
No problem. Like I said, we got lots of questions here, so. Next one, don't. 2 questions. How is pocket pentrometer versus field vane test decided? Is one more costly than the other? That's the first question, and I'll read the second one once you're done that.
So yes, so a field vane takes longer, which obviously time is money. So it is more expensive to do, as well as it's more equipment. So generally the pocket pentrometer, if you're in kind of the cohesive soils, it's no real extra time to just do it on every sample. You're then doing the field vanes kind of at less frequent intervals to confirm the findings of the pocket penetrometer, as well, especially when you're in kind of real soft clay material. That's when you definitely want to do field vane testing. If you're in a very stiff to hard clay, the majority of the time you're not going to be able to even turn a field vane, so it's not going to provide you much insight without if the soils are, I guess you'd say, like kind of half decent. So it's more for when you have poor conditions.
Okay, and please define weathered bedrock. How is it characterized differently versus fractured bedrock, or are they similar?
So you can have they can be similar, but they may be different. I mean, you can have highly fractured bedrock that is not very weathered. But typically your weathered bedrock, there's going to be other indications of it as well on site, like oxidation of the cracks and different things like that. A lot of it comes down to the kind of looking at the cores and assessing the results and seeing it kind of visually in the specific geotech or geologist interpretation as opposed.
Okay. The report indicates, I guess this is the example that you gave. The report indicates that soil is poor or fair. Can you put these into context?
So the poor and fair were used in terms of the bedrock. I believe those were kind of descriptions that you use when based on the RQD. And those are based on what I said there, the RQD. So I believe poor is 25 to 50% RQD, and then 50 to 75 is fair. Put them into context, I mean, you're going to have more strength out of a fair bedrock, but to say what the strength would be depends on what the bedrock type is as well, whether it's a shale or a granite or a limestone. Will play a big factor in that, a lot more than in the RQD, likely.
Okay, thanks. Shall the Geotech report contain information related to frost depth and frozen conditions?
So yes, we typically have that in most of our reports. So like where I work here, most of the area is a 1.2 meter frost depth. So we're specifying that any kind of foundations need to be below 4 feet. Any pipe shallower than that needs insulation, that sort of stuff. In terms of frozen conditions during our investigation, I mean, we'll note if it's frozen, but it does impact, like the SPT can test through frozen ground. You get erroneously high values, which aren't representative, but overall, once you're below 4 feet, you're not going to have frozen ground where we work anyway. So it's not going to be a large issue.
Thank you. What's the lowest N value that you can install pipe on using the typical pipe bedding thickness?
I don't think that's something that it is just like this value, like 4 is the minimum or whatever the case may be. It really depends on the consistency, the depth of that thickness. If you have one real low value and everything else seems okay, that one value may just be a kind of a loose pocket that is easier dealt with. There's no hard and fast rule, I wouldn't say, and it all does come down as well to the specific geotech engineer. One may say look at the exact same conditions, and one may say 4, and one may say 3 or 6, or depends.
Okay, so and would that show up again in the report as far as the pipe bedding recommendation type thing?
Typically, I would expect that to be kind of provided where this area is very low end values and may not be suitable, and this may whatever may be required to rectify that in this area. So typically, yes.
Okay. Is shear vein velocity of soil required? How can it be measured? Shear wave or
shear wave? Yeah.
Okay.
So we perform shear wave velocity soundings. Not on. We don't do it on most projects. I would say we do it on select projects. Where I work though is a very low risk seismic area. If you're in a high risk seismic area, it may be something that is required on every project. I can't really speak to that because it's not my expertise, just based on where I've done the work my whole career. We do it on select projects when we think there's a good chance of increasing the seismic site class for a project. But on most projects, we just base our seismic site classifications on the soil conditions in the area.
Okay. Can you speak to different boring materials, split spoon / wash boring, etc., and the data available for analysis?
So, I mean, the conventional split spooning is what we do for most projects just because it's cost effective. It gets us the results we need. It's more when we're getting into kind of really deep boreholes or challenging conditions for conventional drilling where we would go to kind of a wash boring method, just because there's an increased complexity with that and increased costs. If you're going deep into groundwater below like a saturated sand, you may need to be drilling using wash boring. But yeah, generally we just go with kind of the conventional hollow stem auger and split spooning, just based on the geology we have in the area though.
Very good. Okay, I see that we're up against the clock here and we're only about halfway through the questions, so I apologize very much to all of those of you who have asked questions that we haven't been able to answer. If you would like your question answered, please do reach out to Dan with an email and send him that question directly, please. So I want to thank you, Dan, very much for the presentation today. Lots and lots of interest. Many people still online, so the interest is definitely there. I want to remind people of the CUIIC events coming up, both the Pipeline Rehab Academy, March 21st and 22nd. Take a look on the website, CUIIC.ca, for that, and also the next webinar on spray-in-place lining. So again, Dan, thank you very much.
Thanks.
Bye-bye, everyone. Have a great day.